Today we're going to be talking about open loop op-amp circuits. And for us to understand what an open loop op-amp circuit is, we need to talk very briefly about feedback. So if I have a circuit that looks something like this, where I apply some input voltage, let's call it VN1, and some voltage here, let's call it VN2. Either of those could be AC or DC, doesn't particularly matter. They can also be zero. But if I don't have a path that's connecting my output terminal to my input terminal, this is an example of an open loop circuit. So I could have resistors here. So like I might potentially put a resistance here or here or here. But as long as I don't connect the output terminal to either of the input terminals, it's still an open loop configuration. Now, let's say that I have a similar thing. And in this case, I am going to connect my non-inverting input terminal to my output terminal. And in this diagram, I'm using just a simple generic two terminal element because this could be a resistor, a capacitor, an inductor, a wire, really doesn't particularly matter. But if there is a connection between, say it doesn't matter, that will vastly change how the device works. But from a concept of feedback, it doesn't matter. As long as there is a conduction path between the output terminal and the non-inverting input terminal, we have what's called positive feedback. So let's talk about positive feedback here very briefly as to what some of the effects of that are going to be. Okay. Now, whether or not you realize it, you have all probably experienced a positive feedback situation. Okay. So let me explain explicitly what I mean by that. How many of you have ever been in an assembly or at a conference or anything like that, and you heard a microphone start to feedback? Practically everyone. That is literally a positive feedback situation. Let me explain why that is, okay? So the input of that system is the microphone. The output of that system are the speakers. So what happens is when the speakers output some sound, some of that sound gets picked up by the microphone, which sends it through the signal path again, and it subsequently gets amplified and then over amplified and then over amplified each time it passes through until you get to a point where it just squeals, because it's just the sound waves that are coming out of the output of the amplifier system are fed back into the microphone over and over and over again, okay? That's what positive feedback is. So in an electrical system like we have, positive feedback is going to mean it's going to have two very important consequences, and we're going to see these in action in Wednesday's lecture. The first of which is we have a decreased linear range. I'm going to put as compared to open loop. And one of the things that we learned on last Friday's lecture, when we were looking at an op-amp circuit, which happened to be an open loop circuit, was that it had an incredibly small linear range to start with, right? For that MUA 741 op-amp that we were looking at, its linear range was from 50 microvolts, negative 50 microvolts to positive 50 microvolts in an open loop configuration. This linear range is even smaller. So what is the consequence of this decreased linear range? It will practically always be in either positive saturation or negative saturation. It will pretty much never work as a linear voltage amplifier. So I'm just going to put VN1 here, VN2 here for the sake of argument. We could also load this thing up with resistors and all that kind of jazz if we wanted to. It will kind of affect the behavior, but not much. It's generally always going to behave like this. Move this up a smidge. And then the last type of configuration that we are going to talk about is a negative feedback amplifier. And the negative feedback amplifier is the type that we talked about explicitly in circuits 1. And in a negative feedback amplifier, our feedback loop is on the inverting side of the amplifier. So there is some conduction path between the output terminal and the inverting input terminal. And so effectively in a situation like this, instead of the output being added to the input, causing the output of the system to gradually push towards saturation, now we're taking away a piece of the output from the input signal and dragging that output signal down to some stable operating point. That's the role of negative feedback, right? So in a negative feedback system, we have a significantly increased linear range. And there are a few other characteristics of negative feedback, some of which aren't really going to make sense because we're not talking really about frequency response or anything at this point. But we're going to see that for an amplifier that has negative feedback, it'll have increased bandwidth. Reduced distortion, and a couple of other things, which is why most amplifiers are implemented in a negative feedback configuration. Okay. And we'll talk significantly more about some of the properties of negative feedback in your later classes, particularly in your electronics course when we're going to be designing amplifiers. Okay. All right, so this is the type of circuit that we're going to be talking about today. We already have some idea of how it works because this is the exact same circuit that we analyzed effectively at the end of our last class meeting. So let's talk about an application of an open loop circuit. And that application is commonly referred to as a comparator. So in a comparator circuit, all we are doing is we are comparing an input signal to some reference voltage signal, and then our output will either be high or low, depending on whether our input signal is greater than or less than that reference, okay? So let's look at this circuit here. Let's say that I apply an input signal to the non-inverting input pin. I ground my inverting input. Actually, let's not ground it. Let's put a reference voltage here, which might be 0. Here's VCC plus. Here's VCC minus. And here is V out. So what would our practical op-amp model representation of this circuit look like? Well, something like this. Here's Rn. Here's our open loop voltage gain times our differential voltage. Here's our out, like so. Since our output terminal is open circuited, that means the voltage drop across these two nodes is just going to be AVOL times VD. Connected between my inverting input terminal and ground, I'm going to have some voltage source VREF. Connected between my non-inverting input terminal and ground, I'm going to have my voltage source VN. And as always, my differential voltage VD will be defined as the potential difference between my non-inverting input node and my inverting input node. Okay. So mathematically, the output voltage for this circuit is just going to be AVOL times our differential voltage, which in this case is simply VN minus V reference. Now, technically speaking, we know that this is only true whenever Vn minus V reference as a quantity is within the linear range of the amplifier, okay? So let's make a plot of this output voltage for a few different parameters, okay? So let's say that we're dealing with a mu A741 op-amp again, such that our open loop voltage gain is 2 times 10 to the 5. Our input resistance, which here doesn't particularly matter, is typically 2 mega ohms, and our output resistance here is 75 ohms. So let's say that VCC plus is 5 volts, VCC minus is negative 5 volts, and VREF is positive 2 volts. And we will allow our input voltage to go all the way from negative 5 volts up to positive 5 volts. So if we were to plot our output voltage as a function of our input voltage, we should come up with a curve that looks something like this, right? So let's start way to the left, okay? So let's say that Vn were negative 5 volts. What should my output voltage be in that case? We have a mathematical expression right here that we can evaluate, so this should be pretty straightforward, right? So our open loop gain is 200,000. Our input voltage is negative 5. Our reference voltage is 2. So 200,000 times negative 7 is negative 1.4 million volts, if my mental math is correct. Is that voltage more negative than the supply voltage? Significantly so. So what should my output voltage be? Negative 5 volts. Okay. So out here, at this particular point, let's make this voltage right here be negative 5. This output voltage up here be positive 5. This guy right here will be negative 5. This guy over here will be positive 5, right? So we've got a point there. Now I think it's going to stay negative for quite some time, so let's evaluate it at Vn is equal to 0, with the assumption that if it stays negative, it's not going to just magically change in between because there's no reason for it to do that, right? So if Vn were equal to 0 volts, what would our output voltage be? Still negative 5, right? Because we have 200,000 times negative 2 is negative 400,000 volts, which is still way more negative than our supply voltage of negative 5 volts. So this is still going to be 0, and I can say pretty emphatically that all points in between there will also be at negative 5 volts, because my differential voltage will never be positive in that region, so there's never any reason for it to switch polarities or anything like that. All right, let's look at negative 1.99 volts, right? So that's something just before our reference voltage. Right. So here's our reference voltage of 2 volts right here. What's going to happen when our input voltage is positive 1.99 volts? Calculator. So we're going to have 200,000 times 1.99 minus 2 comes out to be negative 2,000 volts, which is still significantly more negative than VCC minus. Let's look at 1.99 volts. 200,000 times 1.999 minus 2, negative 200. 200,000 times 1.9999 minus 2, negative 20. So realistically, anything below 2 volts, even if it's only a few millivolts below 2 volts, is still going to bring us to an output voltage of -5 volts. Now, what do you think is going to happen when we're at 2.0001 volts or something like that? It's going to switch to positive, right? Absolutely right. So we should see something up here, and then it's going to stay positive for all voltages after that. And what I'm going to do now is I'm simply going to connect these dots. Now, technically speaking, this line connecting here, or our transition from our output going from VCC minus to VCC plus, technically that is not a vertical line. It is just a line with a hugely positive slope. The slope should be on the order of 200,000 volts per volt, the gain, right? So because our input voltage has to be within a couple of microvolts of this reference voltage, we can really just kind of throw that part out. And we can say that the output voltage for this device is simply VCC minus when Vn is less than Vref, and it'll be VCC plus when Vn is greater than Vref. And we call this a non-inverting comparator. So can anybody think of an application where we might use something like this? Really, it's just whenever we want to compare a signal to a particular reference. And sometimes that reference can be zero. So one place that this is very often used is in what are called zero crossing circuits, where a zero crossing circuit effectively just tells you whenever your input signal crosses zero. So the output goes high when your signal gets larger than zero, and it stays high until your signal falls below zero. So this is something that's used very regularly to do power measurements and all of that kind of stuff using microcontrollers, because microcontrollers typically can't take large input voltage ranges. So if we were trying to use a microcontroller to, say, measure the power factor at which a load that's connected to an outlet or something like that is operating at, we couldn't simply just plug our input voltage of 120 volts AC into our microcontroller. That would fry it. But instead, we could use a zero crossing circuit like this to say, well, now our voltage is high, so we effectively know what our phase angle of our voltage is going to look like by time stamping when this transitions from low to high. And then we could do something similar for the current signal, and then the difference between those two timestamps tells us what the difference in phase angle is between them, which and then in turn gives us our power factor, right? So zero crossing circuits use comparators all the time. They can also be parts of analog to digital converters, and we're going to design one of those here in just a couple of minutes. Let's see what would happen if we flip the script slightly. And so all I'm going to do is I'm going to change where I apply my input voltage and where I apply my reference voltage. So here's plus, here's minus, VCC plus, VCC minus. Vref is now being applied directly to the non-inverting input node. Vn is going to be applied to the inverting input node. Here's the out. I'm not going to bother drawing the practical op-amp model here because we should be able to figure out what our output voltage is going to look like by looking at this relationship and then swapping Vn and Vref, because that's literally all we did in our circuit, right? So if I physically swap them in this model, Vd is just going to be Vref minus Vn, right? No need to redraw anything here. So if I were to plot things using the exact same parameters that we had before, where here's my 2 volts reference voltage, here's +5, -5 volts. What do you guys think the output is going to do? Inverse. So it's the inverse, okay, but what do you mean explicitly by that? So I could flip it over the horizontal axis, or I could flip it over the vertical axis. Which one should I be doing? Sure. I was thinking horizontal. So if I flip it over the vertical axis, it would look something like this. Is that what you mean? Give you a hint, that's wrong. Should be this. It's very, very easy to understand why, okay? So when Vn is a negative voltage, or really anything less than 2 volts, Vref minus Vn will be a positive voltage. Our gain is positive, so positive number times a positive number gives us a positive output voltage. As soon as Vn is larger than Vreference, our differential voltage Vd is a negative number. Our negative number multiplied by our positive open loop voltage gain gives us a negative output, right? So it's the exact same curve, except that it's flipped about the horizontal axis. So we can see here really easily then that V out is just going to be VCC plus for Vn less than Vref, and it'll be VCC minus for Vn greater than Vref. And this is how a inverting comparator works. So now let's do a simple design exercise. We want to design a simple analog to digital converter, commonly referred to as an ADC. which outputs a logical high, defined to be V out is equal to 5 volts for Vn greater than 3 volts. And outputs a logical low where V out is equal to 0 volts for Vn less than 3 volts. So this is actually pretty similar to how the Arduinos you guys used in the 120 series, how its analog to digital converter works. So let's start. Are we going to use an inverting comparator or a non-inverting comparator? So do we want our output to be high when Vn is greater than Vref, or do we want our output to be low when Vn is greater than Vref? High when Vn is greater. Right. So let's look at our mathematical relationships. This one says the output is high when Vn is greater, so we want a non-inverting comparator. Okay, so that's our baseline. We want a non-inverting comparator. So our input voltage is applied here. All right. Our output voltage is going to be measured here. So we have one thing there. Okay. So now we need to figure out what our supply voltages are going to be and what our reference voltage is going to be. Anybody have any thoughts? Patrick, you seem to be halfway raising your hand and then you decided against it.
I was thinking about this.
Okay.
Would it be VCC, would that be your VCC plus, would that be 5 volts and would it be 0 volts, VCC 5 volts?
Yeah, absolutely, because those are what our outputs are going to be. And we know for our comparator, our output voltage is always going to be our supply voltage. Yeah. So our output voltages are defined by our supply voltages. So we need 5 volts up here and to ground down here. Okay. So we got 2 more things knocked out. We got 1 other thing to look at. So let's figure that out. What's our reference voltage going to be? 3 volts, because that's what we're comparing our input signal to. It's that simple. Congratulations, you guys have designed a practical circuit that does something. Okay, that's a big deal. Now, let me ask you guys a question. Is there a way for us to get this 3 volts without having just a second voltage source in this circuit? You guys ever heard of anything called a voltage divider? Taking my class, you have. Do it all the damn time. So we are going to establish this 3 volts right here using a resistor network so that we don't have to have a second DC power supply to make this thing work, right? Because realistically, we're probably going to not want to have a whole bunch of different DC voltages that are being supplied by separate DC sources, okay? So let's talk about how we might do that. So I said we were going to use a voltage divider, and so I'm going to effectively add a supply rail here that's at 5 volts And I'm going to add a supply rail down here. That's at ground. And now between these supply rails, I'm going to put some resistors. Okay. So my ultimate goal is for the voltage drop across this resistor down here to be 3 volts. Anybody have any thoughts on how I might accomplish that? I'm trying to make this voltage 3 volts because that will apply 3 volts with respect to ground at my inverting input terminal, and that is the reference voltage that I'm trying to get. Okay. So, according to Kirchhoff's voltage law, absolutely correct. That means there has to be a 2-volt drop over this one. Okay. I got no problem with that because there's a 5-volt total drop across these 2 resistors. How do I make this happen? So the top resistor is a 2 ohm and the bottom resistor is a 3 ohm. So the ratio should be 2 something on top to 3 something on bottom. I agree with that wholeheartedly. We won't use just a 2 ohm resistor and a 3 ohm resistor because the sizes of our resistors very much matter in a practical op-amp circuit. So let's talk about that very briefly here. Okay. So the internal input resistance of an op-amp is on the order of megaohms, right? Which means if we are going to use a resistor network here, we want to make sure that the resistors that we use are significantly smaller than the megaohm scale so that effectively none of our current flows into that terminal, which would mess up our voltage divider relationship, okay? So we need resistors that are significantly smaller than megaohms over here. When we're connecting a resistor across the output terminal of our op-amp, well, the output resistance is typically low on the order of tens to hundreds of ohms. So we need a resistance that's higher than that. So that if we look up here, if I put a resistance here, we want this resistance RL to be much greater than R out so that almost all of the voltage being supplied by this source, almost all of that voltage occurs over this resistor and practically none of it occurs over this one, right? So effectively, the sweet spot for op-amp biasing is kilo-ohm size resistors because they're about 1,000 times smaller than the internal input resistance, and they're about 1,000 times larger than the internal output resistance, so that as long as we're biasing with kilo-ohm size resistors, 95% of the time, everything's going to work out fine, and we don't need to really pay any attention to things beyond that, okay? So with that in mind, if we make this guy right here a 2 kilo ohm resistor, and this guy right here a 3 kilo ohm resistor, we should find out that this voltage right here is approximately 3 volts. So let's model this in LT Spice. I can show you guys how I like to do my op amps and all of that kind of good stuff. So let's get this maybe down here. All right. So the first thing that I'm going to do is I'm going to put my supply voltages in. Okay. So I'm going to have this voltage V1 here. I'm going to put this voltage V2 here. And what I'm going to do is I'm going to wire this in series. And then I'm going to put my ground in the middle. Okay. I'm not required to do this in LT Spice, but this is physically what I would do in the lab to implement a positive and negative voltage from a single supply, right? This is exactly what we did in circuits 1 for our op amp lab. It's what we'll continue to do the entire time we're here. So this voltage is going to be 5 volts, and this voltage is going to be 0 volts. Now, I know it seems weird that I'm including a 0 volt source here. I'm just doing a kind of best practices type thing. I'm going to add another voltage source. This is going to be my input voltage, and I want it to range from 0 to 5 volts. So anybody have any ideas on how I might do that? So because it's changing, it's obviously not just a simple DC voltage source, right? So let's go to the advanced tabs and look at what we have here. So we have pulsed voltage sources, which means I can make it either be a high voltage or a low voltage, but it's not really sweeping across that entire voltage range. My next option is a sinusoidal voltage, which oscillates between 2 points, right? So that seems like a pretty reasonable thing to do. So I'm going to come down here and I'm going to click on sinusoidal. I want it to range from 0 to 5 volts. So what should my amplitude be? 2.5, yeah. So 2.5 volts. I agree with that. But I'm going to need to include a DC offset, because if I just left my amplitude at 2.5 volts, it would range from negative 2.5 to positive 2.5 over and over and over again. And I want to bring that up so that it ranges from 0 to 5. So what's my DC offset? Also 2.5 volts. The frequency here doesn't matter. It just needs to not be 0, because 0 would be DC. So I'm just going to put 1. I don't need any delay or any of that other stuff really. And we're just going to have it run for 1 full cycle. So it'll go all the way from 0 up to 5 and then back down to 0. Okay. Nothing would really hurt it if we allowed it to run more. I just don't want to. I'm going to ground the negative polarity terminal of this voltage source. And then now, separately over here, I'm going to put my op amp. So I'm going to use, and I suggest you use it as well, the component that is called Universal Op Amp 2. And when I give you homework assignments where I make you model op amp circuits, I believe I explicitly tell you, use the Universal Op Amp 2 model. Okay. Now, the reason why we're going to use the Universal Op Amp 2 model is because it's editable, meaning if I right-click it, I can change a bunch of different things. We're not really going to have to change too much in this class, but we can see that it's roughly behaving how we would expect it to be. Our open loop gain here is 1 mega ohm, so that's, or excuse me, 1 meg, so that's 100,000, close enough to, or actually that would be 1 million. We could change that to 0.2 meg if we wanted to. Our input resistance down here, it says it's 500 mega ohms. We could change that to 2 mega ohms if we wanted to, and really it's not going to make much of a difference. And then our output resistance, we really can't change that directly. We would just have to change the limit on the current that can flow out of the output. But anyway, changing those parameters really isn't going to make much of a difference here. What I like about the universal op-amp 2 model is specifically it takes saturation distortion into effect, meaning that the supply voltages will limit our output voltages in this system. If we use the universal op-amp 1, it doesn't take that into account. Universal op-amp 3 and universal op-amp 4 just have more parameters that we can edit, which is really beyond the scope of what we're doing here. So universal op-amp 2 is our kind of sweet spot thing if we're not going to just use a very specific model. Okay. All right. I'm going to give myself a few stubs of wire here. And now I'm just going to use labels. Okay. So this is something that's pretty interesting, I think, and it makes our schematic diagrams look much nicer. So I'm going to call this voltage up here VCC plus, and then I'm going to apply that right here to the positive power supply terminal of the op-amp, which is denoted with this plus sign. So effectively what this is doing is it's saying this node and this node are at the same potential without me having to show a long run of wire to connect that supply voltage to the supply terminal of the op-amp so that it just is going to look cleaner. Okay. I'm going to do something similar here for VCC minus. So this is VCC minus. This is the negative supply voltage. I actually I was about to say I forgot a voltage source, but I very much did not, because we were going to use, and we'll do it with the resistors in a moment. Let me give myself a reference voltage source up here. This is just going to be a DC voltage, 3 volts. Let's call this one Vref, which should go on the inverting input terminal. One thing that I want to note here, the positive supply terminal is on the inverting input terminal side of this op-amp model. The negative supply voltage is on the non-inverting input side. I don't know why they chose to do it that way, but they did. So just make sure that your positive voltage is always on the plus sign, your negative voltage is always on the minus sign there. And then lastly, let's do an input voltage label. So VN will be here and also here. And we'll put V out over here. Okay. So let's run a simulation. Let's do it for 1 second. And let's look at the out here. Okay. And I'll change this color to blue. While we're at it, let's look at the in. And let's change that guy to red. So we can see here pretty easily that when our input voltage is less than 3 volts, our output voltage in blue is low. When our input voltage exceeds 3 volts, our output voltage stays high or goes high and stays high, and it doesn't come back down until our input voltage falls below 3 volts again, right? So this is the behavior that we would expect. Now, this graph looks significantly different, or at least to me, it looks different than the graph that we came up with. And that's because we are plotting both V out and V in here as a function of time. In the graphs that we made to explain how this device works, we had V out plotted as a function of V in. We can do that in LT Spice if we mouse over our horizontal axis and right click. Right here where it says quantity plotted, this is our independent variable. This is what's on our x-axis. So we can change this from time to our input voltage. And so I'm going to say I want the voltage at node V in. Press OK. And now the blue curve is my output voltage, and I can see very easily that when my input voltage is less than 3 volts, my output is low. When my input voltage is greater than 3 volts, my output is high. I also have this red line right here. This red line is literally V in as a function of V in. It's just a line with a slope of 1. It is giving us no information whatsoever. So it's probably best for us to just delete that one. And now it looks exactly like what we would expect for a non-inverting comparator. Okay. So we got this to work using voltage sources and all of that kind of good stuff. Now let's restructure this by using the resistor network. So let's delete a couple of things. I'm just going to put a rail of wire up here. And similarly, I'm going to put a rail of wire down here. I'm going to connect the positive power supply to this top rail. The negative supply to this bottom rail. And then I'm just going to reuse those labels, VCC plus and VCC minus. Like so. If I'm not mistaken, earlier we said that this one should be a 2K and this one should be a 3K. And let's rerun our simulation. So here's our output voltage, and let's make it be as a plot of our input voltage. And change that to blue so it's easier to see. And we effectively get the exact same curve. Okay. If we wanted to, and I do, I can mouse over this node. And I can see that the DC operating point of this node is 2.9997 volts. So it's not exactly 3 volts because our op amp is going to leach an incredibly small amount of current, but it's close enough to 3 volts for it to not really matter to us. Okay. If we were to do something like put mega ohm sized resistors here, now our curve has changed appreciably because our reference voltage is significantly away from that 3 volts, right? If we look at our DC operating point, our reference voltage is now at 2.8125 volts. This is because Now our op amp is pulling a significant amount of current because when the current flows through here, it sees a mega ohm size resistance down this path and a mega ohm size resistance down this path. So we're not limiting the current that's flowing into the op amp in this particular way, right? So that's why choosing the right size of resistor values is so incredibly important when biasing op amp circuits. All right, so I want to do one last thing. I'm going to add some noise to this and show you that in some applications, a comparator isn't the best tool for the job in doing a comparison like this. And that'll introduce us, or that'll show us why we're going to use positive feedback on Wednesday's class meeting. So what I'm going to do is I'm going to add another voltage source. Put it up here. And then I hope I can remember, actually. I want I think this is the right one. We'll find out in a second. So I just used a behavioral voltage source here, which is just a fancy term for a dependent source where my voltage is just going to be a function. I'm just going to have this generate some white noise effectively. So that might look like something like V is equal to white 2e to the 6 times time or something like that. It's just randomizing noise here if I'm remembering how this works correctly. I'm going to wire these in series so that I'm just adding a little bit of noise on top of my sinusoidal input. And now I'm going to call this guy up here my input. Let's close this, resimulate. Let's look at what the voltage at this node looks like. Yeah, so that's a nice noisy input signal. Right, so we can see that it's still going from effectively 0 here-ish to 5 here-ish, but there's some noise added on top. This is a pretty significant amount of noise. If we look at our output voltage, what's going on right here and right here is that our comparator effectively just makes a simple decision. Is the input voltage greater than Vref? If so, make it go high. If the output voltage, or excuse me, if the input voltage is less than Vref, make it go low. Well, if the output voltage, or excuse me, if our input voltage has noise, then it's going to cause the output to oscillate, because instead of having a smooth transition from below Vref to above Vref, it might go from below Vref to above Vref to back below to back above really quickly and all that kind of stuff. And so we see this ringing and oscillation, so our output signal isn't stable. So we are going to correct this by using positive feedback at the beginning of Wednesday's lecture. All right, so that is enough out of me for today. So if you guys have any questions, I've still got 15 minutes that I'm supposed to be here to answer them. And if not, I'll see you guys on Wednesday.